Although we dream of colonising the moon, travelling around the solar system and one day beyond to the stars, space is a dangerous place, not least because of the radiation from our sun and galactic cosmic rays. We only found out about the bands of trapped ionizing radiation that surround the Earth, Van Allen belts, just after the launch of Sputnik, and these have been a fertile ground for the moon hoaxers ever since, claiming that they are so dangerous that no one could ever get through. But as we venture deeper into space for much longer duration missions like those to Mars and beyond, how do we protect the spacecraft, the crews, the control electronics and computers from radiation? This video is sponsored by Magellan TV. Now, Magellan is a new documentary streaming service run by filmmakers, which is something I can appreciate because I do the same thing and I know what it takes to make something that's interesting, engaging and something you believe in. Be that about history, science, space or nature, and that's what I see when I watch documentaries on Magellan. If you're finding you have some more spare time on your hands these days, Magellan has 2,000 plus documentaries available, with more being added each week, and a wide selection of those being in 4K for no extra cost, or you can stream them directly to your smartphone or tablet wherever you are. If you're watching this, then you're probably interested in more space videos, and I have a couple I can recommend on Magellan TV. The first one is Faster Than Light and looks at what it would take to get to the newly discovered exoplanets around nearby stars, and the second is Powered by Space, Reinventing Spaceflight, about using plasma as the future for rocket engines in the solar system. And now you can watch these and many more by getting your 1 month free trial by going to the link for this special offer right at the top of the description below. And I know you'll find Magellan TV as worthwhile as I have. When most people think of radiation, X-rays, nuclear power and atomic bombs normally spring to mind. All things that we need to be relatively close to be affected by. But in space, the radiation comes from millions or billions of kilometers away, and often much farther. The sun is the biggest source of radiation in the solar system, emitting both electromagnetic radiation like X-rays and some gamma rays, but also a huge amount of charged particles, the nucleus of atoms with the electrons stripped away, as well as the electrons themselves. The other source of radiation are galactic cosmic rays. These are mostly gamma rays and high-energy charged particles that were created in events like supernova explosions, thousands or even millions of light years away. These types of high-energy radiation are called ionizing radiation because when they strike a normal atom, they have enough energy to knock the electrons off, leaving just the nucleus, which is then called an ion. This is where it becomes dangerous to us and electronic equipment we use to control and fly spacecraft with. When electronic devices are exposed to ionizing radiation, a single charged particle can knock thousands of electrons loose, which creates electrical noise, and in modern digital chips like CPUs and memory chips, it can cause transistors to turn on and off, changing the bit data from a 1 to a 0 or vice versa, scrambling information and causing things like computer crashes. With a high enough or long enough dose of radiation, the chips are physically damaged and stop working correctly. Since Apollo, control system computers in spacecraft use radiation-hardened components and have redundancy built in, because it's thought that in normal operation it's highly unlikely that both the main and backup system would have the same error. This type of redundancy was built into the IBM flight computers that controlled the Saturn V rockets, which we also have a video on if you're interested. In the human body, these ionizing particles act like tiny subatomic bullets, which can break apart chemical bonds, kill cells, and damage DNA, leading to cancer. At low levels, like the background radiation we live with every day, the damage is not a problem, because the body can replace the damaged cells easily. It's when the radiation level rises that it becomes a problem, and it also varies depending upon the amount of energy the charged particles are carrying. But in general, the total cumulative dose is where it matters. A moderate dose over a long period of time can cause more damage than a single, very short high dose, as the body is unable to repair the consistent ongoing damage fast enough. This is why it's okay for you to have an X-ray every so often, but why the radiographers are behind shielded doors and glass to keep their cumulative dose as low as possible. You might not think it, but astronauts are radiation workers too. Once out in space, they're exposed to higher levels than they are on the Earth, because the radiation can go through the walls of a spacecraft they're in. Astronauts on the International Space Station wear dosimeters to measure their accumulated amount. Though the ISS stays relatively close to the Earth and is protected by the Earth's magnetic field most of the time, once they have reached their lifetime radiation limit, their job as an astronaut is over. This is due to the increased risk of cancer that any continuation of that work would give them. However, the ISS also regularly flies through the South Atlantic anomaly. This is where the Earth's inner Van Allen radiation belt comes closest to the Earth, and the radiation levels can become much higher. The Van Allen radiation belts are areas where charged particles, mostly energetic electrons and protons which come from the Sun, as well as galactic cosmic ray particles, are trapped by the Earth's magnetic field. When the Apollo mission went to the Moon, they knew about the radiation belts, but chose routes that would take them through the least dense areas with the lowest levels of radiation, and they were only in them for a couple of hours, going there and coming back, with time in between for the body to recover. The outer skin of the command modules in the Apollo missions were made from a stainless steel sheet with a honeycomb structure in between and lined with fiberglass. The inner pressure shell was made from a similar honeycomb structure, but this time made from aluminium, which might not sound like much, but it did work. Counter to what many think, having a thick metal shield like lead in a spacecraft could actually make things worse, as well as making the craft too heavy to get into space. This is because of the Bremsstrahlung Effect. When a charged particle hits another charged particle, or the nucleus of an atom, in this case the skin of the spacecraft, it slows down. This releases energy in the form of X-rays, which then go on to affect the crew or the equipment. The best way to shield against charged particles is to use a material with a high hydrogen content that absorbs them. In the original Apollo command module design, a tetrafluoroethylene plastic tissue was used in the ionizing chamber walls to help absorb these particles, but it was also flammable, and this helped the fire spread in the Apollo 1 accident that killed the crew of Gus Grissom, Ed White and Roger Chaffee. Afterwards, to reduce the fire risk, aluminium was used in place of the plastic tissue, even though this was not ideal from the Bremsstrahlung point of view. But in recent times, a new approach has been developed using Z-graded materials. The idea behind this is that you have several layers of material which get progressively lighter by their atomic number from the outside in. There might be a tantalum outer layer, with other layers such as tin, steel, copper through to aluminium or polypropylene and boron carbide as the innermost ones. This graded shielding would scatter the protons and electrons as well as absorb gamma rays. Each of the layers would absorb the X-rays created from the Bremsstrahlung effect by the previous layer, and the boron would absorb the neutrons. In the end, the amount of radiation would be lowered to a safe level, but requiring less of it compared to a shield comprising of a single material. The most effective way to shield a spacecraft is with the simplest of materials, water. This is because it's 2/3 hydrogen. Water is so effective at reducing radiation that it's used to store highly radioactive nuclear fuel rods. For every 18 centimeters of water, the radiation is reduced by about half. A cylinder of water around the crew quarters, about 1 meter thick, would give enough protection for a crew on the journey to Mars for 6 months or so, but they would have Earth-like levels of radiation over the transit time. The only problem with this simple solution is that water is very heavy, with 1 cubic metre of water weighing at about 1,000 kilograms. Providing a 1 metre thick shield for a tube-like crew quarter measuring 5.5 metres by 22 metres would weigh well over 300 tonnes, greatly increasing the number of launches required to get the mission into orbit, plus the extra fuel that would be required for the acceleration and deacceleration of the extra mass once in space. Another method which is being looked at is to create a magnetic field like the one around the Earth, but around the spacecraft itself using superconducting magnets. This would be effective against charged particles, but it wouldn't have any effect against X-rays or gamma rays, so you would still need traditional shielding methods too. So, for the foreseeable future, we are going to be using shielding which is as light as possible, but with the best possible shielding and absorption characteristics. This basically means that it will do just enough to protect the crew to perform the mission safely, but with little margin for unexpected events like solar flares. So what do you think about radiation issues that future astronauts will face? Let me know in the comments. So thanks for watching, and don't forget to subscribe, click the bell notification, thumbs up and share.